Hey everybody, this is the lecture on section 4.3, which is on separable differential equations. Or differential equations. So, as we were saying before, a first order differential equation is separable when it is of the form y prime equals f x g y. Okay, so for example, y prime would equal to minus y over x, which is one that we looked at in section 4.1, is separable because, well, it's not exactly written like that, but you can just rewrite it as such. Minus 1 over y, minus y times 1 over x, right? So now it's written as f of x times g of y. A non-example, y prime equals y minus x is not separable. So that was one of the other differential equations that we looked at in section 7.1. Or in 7.2, we looked at the direction field for this guy and for this guy. Right? So we've been using those differential equations for a little while now. Alright, but now when you have a separable differential equation, okay, we solve as follows. So you write dy dx for y prime is fxgy, and then, give me a moment. You write dy dx for y prime is fxgy, and then you separate the y's on one side, the x's on the other. So you have 1 over g of y dy is equal to fx dx, and then you just take the antiderivative, that's g of y, is antiderivative fx dx, and then solve for y if possible. Okay. However, you can't always solve for y in these situations. So, for example, did we do that already? I think we did. I don't remember doing the solution of this one. So, given this one, y prime equals minus y over x, we write dy dx is equal to minus y over x. So, minus 1 over y is equal to 1 over x dx. Taking antiderivatives, y dy is 1 over x dx. The antiderivative here is the negative of natural log of y is equal to natural log of x. You know what? Let me leave the negative over here. Make that one positive. Put the negative over here. Plus c. Alright, so this is a solution, general solution, for y as a function of x implicitly. Okay, but we would like to have it explicitly. You can't always get it, okay, but if you can, we want it that way. So we solve for y however possible. So this one is e, use that exponential function, e to the natural log y equals e to the natural log x plus c. This becomes 1 over, or sorry, this becomes just absolute y is equal to, and then we separate this into two factors, like that, right? Now, to get rid of this absolute value here, we just write y equals plus or minus e to the c, e to this, and I'm going to write e to the ln x to the negative 1 power. Right, because you multiply these exponents here. Okay? Now, c is an arbitrary constant. So e to the c is an arbitrary constant. So plus or minus e to the c is just an arbitrary constant. Okay, plus or minus e to the c is just an arbitrary constant. Write it as just a. So y is equal to a, right? E to the ln x, right, is just absolute x to the negative 1. Okay, and so y is equal to a over absolute x. Right, but that means y is equal to plus or minus a over x itself, but, you know, that's just makes a arbitrary constant. Again, it starts out as an arbitrary constant. You don't know if it's positive or negative, so flipping it from positive to negative makes it no less arbitrary. Okay, so that's your final solution. Final general solution, where a is an arbitrary constant, final general solution, explicitly a function of x. All right, let's try another one. So here, y prime is equal to 6x squared over y squared plus 1. So dy dx is equal to 6x squared over y squared plus 1. So y squared plus 1 dy is equal to 6x squared dx. Antiderivative on both sides. So I have 1/3 y to the third plus y is equal to 2x to the third plus c, and there's no way to solve for y here. Right, so you have to leave this one explicitly as a function, implicitly as a function of x. So this is a general solution with y implicitly a function of x. Okay? So how about this now? So that's the general solution. Now, what if you're asked to find specific solutions? When you're asked to find a specific solution, so find the specific solution to y prime is minus y over x, satisfying the initial condition y of 1 is equal to 1. Okay, that is, passes through the point 1, 1. Okay, find a specific solution whose function passes through the point 1, 1. So when x is 1, y is 1. Right? Well, the general solution that we found from the previous example, right, was y was equal to a over x. Now using y of 1 equal to 1, so y is 1 when x is 1. Right, now using that we get this. Right, which is just saying that 1 is equal to a. So the specific solution is y equals 1 over x. Okay? So if they want a specific solution, you just use that, you find the general solution first, and then you use that initial condition to figure out what the arbitrary constant is supposed to be. Okay, so differential equations are most often used for representing various aspects of physical systems. So separable differential equations, here's a classic one. So we've got a large tank holds 1,000 liters of salty water. Initially, there is 15 kilograms of salt dissolved into the water. Okay? Water containing 0.25 kilogram per liter of salt enters the tank at a rate, actually that's pretty high, let's see, 0.10 kilogram of salt enters the tank at a rate of 10 liters per minute. Liquid drains from the tank at 10 liters a minute as well. Assuming that the mixture is uniformly salty at all times, answer the following questions. A. Find a differential equation describing the rate of change of salt Find a differential equation describing the rate of change of salt in the tank at t minutes. Okay, so the variables here are going to be, I don't know, S and T. S is salt, T is minutes. Okay, so let's take care of that just for now. Okay, so let's analyze what's going on here. So we've got this tank that's got 1,000 liters of liquid. Okay, so 1,000 liters of liquid. And the liquid is coming out of the tank at a rate of 10 liters a minute. And liquid is coming into the tank at a rate of 10 liters per minute. Alright, so there's 10 liters a minute coming in, 10 liters a minute going out, so the water stays at, the liquid, amount of liquid in the tank stays at 1,000 liters. Okay? So, first let's find the differential equation. Okay, part A. So and make sure you define your terms carefully. Let's let S of T, so S is a function of T, equal the number of kilograms of salt in the tank at T minutes. So if we let S be the number of kilograms of salt in the tank, then the derivative, ds dt, right, is kilograms per minute, how the amount is changing. So, ds dt, or s prime, is equal to the rate of change of salt in the tank at t minutes. And what are the units? At t minutes in, well, the units are what? T is in minutes, K is in kilogram. So this is in kilograms per minute. Right? Kilograms per minute. So that's the sort of differential equation that we're aiming for. ds dt is equal to something. Right? And remember, that's in kilograms per minute. S of t is in kilograms. Right? Because that's what the problem is outlining. Right? A large tank holds 1,000 liters of salty water with 15 kilograms of salt initially dissolved into the water. Okay? Alright, so what's the differential equation? Well, ds dt is equal to, right, the rate of salt coming in incoming minus the rate of salt outgoing, right? The rate coming in minus the rate going out. So ds dt is equal to what is the rate of salt coming in, right? And we're looking for kilogram per minute. And this is supposed to be in kilogram per minute. So pay attention to the units and make sure you're only using those units that that add together, the same units. You're not adding together different types of units. All right, well, what's the salt coming in? Well, we got 10 liters a minute of salt coming in, and that salt has what? 0.10 kilogram per liter. 10 liters per minute of 0.10 kilograms per liter. Now we want kilograms per minute. Well, kilograms per liter times liters per minute gives you kilograms per minute. The liters cancel out, right? That whole label canceling thing. Right, so we got 10 liters per minute of liquid coming in with concentration of 0.10 kilogram per liter, right? And the liters cancel out and you get kilograms per minute. Minus, well, the rate of salt outgoing. Well, what's the rate of salt outgoing? So you have also 10 liters a minute coming out. 10 liters a minute coming out. So we're going to do the same thing, right? We got 10 liters a minute coming in at 0.10 kilograms per liter. And now we got 10 liters a minute coming out of what in terms of kilograms per liter? How many kilograms per liter? Well, the amount of kilograms the amount of kilograms that there is of salt in the tank is S. Right? S is in kilograms. Kilograms of salt. All right, so that's S over, well, how many liters? All right, 1,000. All right, the salt coming out, right, you have so much salt, S. You have S kilograms of salt in the tank. And 1,000 liters, S kilograms of salt dissolved into 1,000 liters of water. Right, so the amount coming out is S kilograms per 1,000 liters. So that's in kilograms per liter. Right, and that's where we assume this universally salty mixture, because the stuff coming in here may be more or less salty than the stuff that's over here, but you assume it's all uniformly mixed. Okay, which may or may not be reasonable given your system, but here we're gonna do it that way. So there's that differential equation, right? So we've got ds dt is equal to, well, 10 times 0.1 is 1 minus 10 over 1,000 is 1/100th S. So there's the differential equation. Okay, so part B, so that's part A. We found the differential equation. Part B, solve the differential equation. Differential equation to get a function measuring the amount of salt in the tank at t minutes. Right? So what do we have? We have ds dt is equal to 1 minus 1 over 100th of S. No t's, it's just s's. So this is 1 over this whole expression here minus, so it's 1 minus 1 over 100th s, right, is ds is equal to dt. So the antiderivative of 1 over 1 minus 1 over 100 s ds is equal to antiderivative of 1 dt. Okay, well the antiderivative over here is just t plus c. For the antiderivative over here, right, we would like g prime over g. Right, but I don't have this in the form g prime over g. In order to get it in the form g prime over g, right, the derivative is of the bottom here is minus 1 over 100, so I got to balance that out up front by putting a minus 100. So the antiderivative here is minus 100 natural log 1 minus 1 over 100 s equal to t plus c. Okay, so now we're going to use, well, first let's divide by that 100. We need to solve for s now. Right? We always solve for s if we can, and here we can, using that exponential function here. So this is minus t over 100 plus, and just leave it as c. And it's c divided by negative 100, but, you know, it's still an arbitrary constant, so it doesn't really, you know, it doesn't warrant any, you don't have to write it like this, right? C is an arbitrary constant, so when you divide it by 100, it's still just as arbitrary as it was. Now using that exponential function, e to the natural log 1 minus 1 over 100 s is equal to e to the minus t over 100 plus c, right? So absolute value 1 minus 1 over 100 s is equal to e to the c times e to the minus t over 100. Getting rid of absolute values, you get the plus or minus here, right? So we get 1 minus 1 over 100 s is equal to, well, it's just an arbitrary constant, plus or minus e to the c, e to the minus t over 100. Okay, I'm going to move things around. So I've got 1 over 100 s is equal to 1 minus a e to the minus t over 100. So s is equal to 100 minus, well, when I multiply by 100, it's still arbitrary, so I'll just leave it as a. You don't have to keep changing the name of the constant. So there it is. There's the general solution. That's the general solution for this differential equation, which, you know, gives you the amount of salt in the tank at t minutes in kilograms. Okay, but we don't want a general solution. We want a specific solution. I mean, we want to know exactly how many kilograms there are, not, you know, how many kilograms there are, give or take, this constant A. Okay, well, we need an initial condition. I'll do it over here. So now we need an initial condition to find the value of A. So in the problem, it states what? That initially there is 15 kilograms of salt dissolved into the water. So S of 0 is 15. So there's your initial condition. S of 0 is equal to 15. Alright, so we use that. So 15 is equal to 100 100 minus a e to the 0, which is 1. Alright, so a is equal to 100 minus 15 is 85. So s of t is equal to 100 minus 85 e to the minus t over 100 kilogram of salt. Right, so that's our function right there. Measuring the amount of kilograms in the salt, kilograms of salt in the tank at time t. All right, well, this is kind of an interesting function. This is known as a logistic function. And so C, let's ask the following question. What is the trend for S of t as time goes forward? Right, in other words, right, what is the limit as t goes to infinity of S of t? Well, it's right there. It's 100 kilograms. Right? The limit as t goes to infinity of S of t is the limit as t goes to infinity 100 minus 85 e to the minus t over 100. But e to the minus infinity is 0. Right? This is, let me rewrite it. It's the limit as t goes to infinity 100 minus 85 over e to the t over 100. Right? And this goes to infinity. So that's 100 minus 0 is equal to 100 kilogram. And of course, right, at 10 kilogram, or sorry, at 0.10 kilogram per liter, 1,000 liters of salty water contains 1,000 times 0.10, which is equal to 100 kilograms of salt. Right, and that's exactly the concentration of salt that's coming into the tank and that incoming faucet. All right, that incoming faucet has got 10 liters per minute of, what's the concentration? 10 kilograms per liter. No, sorry, 0.1 kilograms per liter. 0.1 kilograms per liter times 1,000 liters gives you 100 kilograms. And that's the trend as time goes on, that whatever's coming in, this constant concentration of salt, will be the concentration of the salt in the tank, after this stuff is coming out. And the graph of such a function looks like this. So here's 100, here's 15, and the function looks like that. S of t. That's called the logistic growth curve. So you can have logistic growth, or you can have logistic decay, like that. You have some sort of upper bound, and then the logistic curve approaches it and has that upper bound as an asymptote, or this lower bound as an asymptote. So logistic growth, logistic decay. So those come up a lot. The other situation that comes up in is in Newton's law of cooling, which also there are some examples in the text, which we'll do later during the discussion. Okay, so that's all for the lecture on this section.